Okay, so my name is Brian, and I'm going to do my presentation on the power of I. I'm not going to talk about myself this whole time. I'm actually going to be talking about the imaginary number I. Now, you may be saying to yourself, imaginary numbers? What are imaginary numbers? I've only dealt with like real numbers all my life, like 1/2 and 1 and 2 and 3 and 87. I haven't heard of I before. What's I? And so I is called a complex number, and complex number takes on the form of a plus bi here. And so the real part is a, and usually that's constituted in textbooks as the capital RE, and then it's closed in square brackets, and then it lists out the real part, and the imaginary part is usually labeled as a capital IM, and then it's squared bracket as an imaginary part. So the A part is the real part, and the B plus BI part is the imaginary part. And so you're like, okay, now I know what a complex number is versus a real number. Now, why is a complex number useful? To get really at the backbone of that, we need to understand, well, what is really like I, really? And so I is defined as the square root of -1. And the square root of -1, when I square it, it's just going to be -1. Whenever I take the square of a square root, let's say the square root of 3, I get 3, right? Same thing with the square root of -1. If I take the square of square root of -1, it's going to equal -1, as we see here. When I take I to the cubed, people are usually smart about this and just split I cubed up into I squared and I, and we get the result of negative square root of -1. And then you go, okay, I'm going to take I to the 4th, and then you get 1, because I squared times I squared equals -1 times -1, which just equals 1. They're like, oh, okay, that's cool, that's fine. It goes from, you know, the square root of -1 to 1. Okay, let's go further down into the line here. So when we do I to the 5th, we get the square root of -1 again. And continuing down the line, we see that a correspondence happens between the two numbers, right, on our charts here. And so we get this pattern, right, in which the i's are going cyclical to all each other, and they're going in patterns of 4, with the exponent here, such that I to the 4th and I to the 8th are the same, or I to the 3rd or I to the 7th is the same. So it goes in process of 4k. And so when that happens, we can say that I has a cyclical representation of 4k. So we can take an example of, well, how about if we have an exponent that's a really, really large number, right, like 87. And so basically all we do is take 87 mod 4, and we get I to the 3rd, which will equal negative square root of -1. And so that is a very good example, right, if you have a really big power to I, what it can equal out to. Now, I'll have Jacob explain some more properties of how I is interesting.
Alright, so for the multiplication of I, say you have C over A plus BI, to get rid of that I, what you're going to do is multiply by something called the conjugate, which would be A minus BI over A minus BI. What's going to happen is you're going to cancel out a lot of things, particularly the I, because I is just square root of -1, so that times itself is I squared, which is -1, which will make that minus sign for the A minus BI into that plus you see at the bottom, so your result would be A squared plus B squared. Pretty simple example of a multiplication of an I function. And there's a thing called the de Moivre property or formula, and that is e to the I theta. And what that, the result of that is just cosine theta plus I sine of theta. And what that does is actually rotate a function along a certain point. So say you have like the line y equals x, you apply that formula, you're going to rotate it 45 degrees counterclockwise. So for any point, say you plug into that new formula, including the de Moivre, e to the I theta, you're going to get a straight vertical line. So you imagine the line y equals x, rotating at 45 degrees, it's going to be straight on that y-axis. Okay. And we see this, you can use this in applications, differential equations, especially engineering. For example, car brakes, like the springs, when you apply your car brakes, it's going to oscillate up and down and eventually dampen out. I mean, this is an example using the de Moivre formula. And I know there's a lot of other research, including Riemann surfaces and the Dirichlet problem, which incorporate complex numbers especially as well.